Why is it so difficult to get to Pluto? This dwarf planet is more than 6 billion kilometers from Earth, and the only spacecraft that has managed to observe it directly was New Horizons on July 14, 2015. However, this ship did not enter orbit around Pluto. It observed it once and continued on its way to the far reaches of the solar system. But why spend so many resources just for a straightforward approach to Pluto? For many years, Pluto was considered the 9th planet in the solar system and the farthest of all. Located at the far reaches of the realm of the Sun, it seemed that it would take centuries for humanity to reach this small world. However, the first opportunity to visit Pluto came much earlier than most scientists imagined. It was the year 1964 when the scientist at the JPL laboratory of NASA called Gary Flandro realized that between 1976 and 1978, there would be a gap of approach between the gaseous planets. So if a space exploration probe was launched on those dates, it could visit most of the outer planets using a series of successive gravitational assists, taking advantage of the unusual planetary alignment that occurs almost every 2 centuries. Shortly after, NASA launched an ambitious project called Grand Tour, which would be starring 2 twin TOPS probes, although in principle they should be 4. One of the probes would be launched in 1976 or 1977 to explore Jupiter, Saturn, and Pluto, while the second would visit Jupiter, Uranus, and Neptune. According to NASA's plans, the encounter with Pluto would occur in 1985 or 1986. After analyzing the ambitious Grand Tour project, NASA concluded that its cost would be too high, so the Grand Tour project and the TOPS probes were canceled. Shortly after, NASA would launch a new, more modest and less expensive project, and from there would arise the famous Voyager exploration probes. Voyagers were initially scheduled to follow the same trajectories as the Grand Tour project, and NASA retained the option of sending Voyager 1 to Pluto after it visited Saturn. If the mission had been approved, Voyager 1 would have flown by the Pluto system in the spring of 1986. Instead, NASA preferred to send the probe closer to Titan, Saturn's largest moon, rather than Pluto. So once again, any visit to Pluto was canceled. Why were missions to Pluto canceled again and again? The reason is simple. Pluto is too far away. A challenge for the technology of the time. The Voyager probes did not have solar panels since they were intended to explore distant planets. In those regions, the solar radiation was very low, and a solar panel could not supply enough energy. Instead, the probes had nuclear batteries that produced electrical energy from the thermal radiation emitted by a radioactive compound. NASA concluded that due to natural wear and tear, this source of radioactive energy could eventually be exhausted long before reaching Pluto. So instead of losing the spacecraft, it was decided to take the opportunity to visit Titan. No one expected that after visiting Titan, Voyager's power source would still work. It was simply a stroke of luck. After these missions, NASA declared that Pluto was a lonely, small, and distant world, so the ships that visited in the future necessarily had to be complex and very expensive. Many scientists thought it was better to spend that money on studying the giant planets and their dozens of satellites, so the 9th planet would have to wait. During the 80s, no serious proposal to explore Pluto emerged, although there were undoubtedly exciting projects. The most curious of these was the Interstellar Precursor Mission (IPM) study of the Jet Propulsion Laboratory (JPL). The IPM mission aimed to send a massive probe to the heliopause, the solar system's edge where the solar wind gives way to the interstellar medium, in a relatively short time. The probe would have a mass of about 90 tons. Yes, you heard correctly, 90 tons. That is the heaviest exploration probe in history, and therefore should be assembled into Earth orbit by more than 5 space shuttle missions. This spacecraft would be equipped with a nuclear reactor and use an electric propulsion system, NEP, with ion engines. And what relationship did IPM have with Pluto? Well, this had to carry a probe to study the 9th planet that would separate when passing through its vicinity. The orbiter would be similar to the Galileo probe for studying Jupiter. It would use a propulsive stage, that is, a rocket to reduce its high speed and place itself in orbit around Pluto, which would hopefully take place during the first decade of the 21st century. As you may be imagining, this never saw the light, since once again the cost of such a project would be exorbitantly high. Sparked the spark of curiosity. In 1989, Voyager 2 had its encounter with Neptune. This event revived interest in a mission to Pluto, since this was the only planet left to explore. In addition, Triton, Neptune's largest moon, had turned out to be a complex world with an atmosphere, polar ice caps, and nitrogen geysers. Observations from Earth indicated that Triton and Pluto shared a common origin in the Kuiper Belt, and therefore must be very similar, especially since it was discovered in 1988 that Pluto was also shrouded in a tenuous atmosphere. In addition, in 1978, Pluto's first moon, Charon, was discovered, so a probe could now explore two worlds for the price of one. A mission to Pluto once again climbed the scientific community's priorities. One of the first proposals was the Pluto 350 mission. The name referred to the weight of the spacecraft, which should not exceed 350 kilograms, including the radioisotope generator, RTG, to produce energy. Pluto 350 was born 2 months after Voyager 2's encounter with Neptune. It was to include only 4 instruments: a camera, an ultraviolet spectrometer for the study of the atmosphere, a radio experiment to observe the atmosphere mainly, and an instrument for plasma analysis. Among the architects of the mission was a planetary scientist named Alan Stern, who would be a key piece in the history of Pluto's exploration. Scientists feared that the dwarf planet's atmosphere would freeze as the planet moved away from the equinox that had occurred in 1987, so the launch should take place as soon as possible. Like the rest of the spacecraft proposals to Pluto, the Pluto 350 mission was to fly by Jupiter to perform a gravitational assistance maneuver, and thus reduce the flight time by 2 or 3 years, depending on the launch window. To place the ship on a direct trajectory to the gas giant, the mission had to be launched by a large rocket, a Titan III or a Titan IV, which was the most potent American launcher at the time. However, this requirement increased the cost of the mission. Paradoxically, the Pluto 350 mission suffered rejection from NASA for being too simple. This is because many scientists and engineers claimed that launching a 350-kilogram probe into the outer solar system was a recklessness that had no chance of success, considering that previously the Voyagers had a mass at launch of about 800 kilograms. In other words, NASA preferred a more complex and expensive mission, but with a guarantee of success, than a simple mission, but with the possibility of failure. Missions that never saw the light of day. In an area of meager budgets, NASA focused on simple flyby missions. In 1992, JPL's Robert Stale went further and announced the Pluto Fast Flyby (PFF) mission, a tiny mission compared to anything that had been done until then. If Pluto 350 were once a small probe, PFF would be tiny since its mass would be less than 150 kilograms. A few years before, few believed such a probe could be built, but with the constant cuts to NASA's budget, these new low-cost missions became almost the only option. Years later, NASA rejected the Pluto Fast Flyby mission proposal and replaced it with a new mission called Pluto Express. Since David Jewett and Jane Liu discovered the first body in the Kuiper Belt in 1992, it was becoming increasingly apparent that Pluto was not a planet like the rest, but a member of this new family of trans-Neptunian objects. For this reason, the mission would be baptized as Pluto Kuiper Express, PKE. At 175 kilograms, PKE would be slightly larger than Pluto Fast Flyby at 140 kilograms and carry 9 kilograms of scientific instruments, although its design was similar. Ultimately, both Pluto Fast Flyby and Pluto Kuiper Express were cancelled due to budget cuts, but a mission to Pluto remained a scientific priority, as the launch window from 2001 to 2006 was inexorably approaching, and then there would be no other chance. So, in desperation, in 2000, NASA created a public contest to choose a mission to Pluto. This strategy had worked very well on low-cost missions called Discovery, but never before had such an expensive probe been attempted. Since the mission to Pluto required a more expensive mission than a Discovery-type mission, but cheaper than a flagship mission, NASA decided in 2002 to create the New Frontiers category for this type of probe. This is how, on February 5, 2001, the winning proposal was the New Horizons. At first, it would carry 4 scientific instruments. These would be Percy, which included the Alice ultraviolet spectrometer, the MVIC color camera, the LISA infrared spectrometer, REX, a radio experiment, LORI, a black and white telescopic camera, PATH, for the study of particles. To reduce the mass and cost of the probe, the corners of the triangular structure were trimmed and the diameter of the antenna had to be reduced from 3 to 2.1 meters. The final mass of the vehicle reached 478 kilograms. The total cost of the mission would be $646 million in 2014. The probe was launched from Cape Canaveral on January 19, 2006. New Horizons approached Jupiter between February and March of 2007 to take advantage of the planet's gravitational assistance, and thus acquire a speed difference of about 4,023 meters per second, or 14,482 kilometers per hour. In July of 2013, the probe sent back the first images in which Pluto and its largest satellite, Charon, can be distinguished as separate bodies. As New Horizons approached Pluto, the images sent back gained resolution. Until the day everyone expected on July 14, 2015, the New Horizons probe passed 12,500 kilometers from Pluto's surface at a relative speed of 49,600 kilometers per hour, taking the sharpest images it had ever seen of what was once the 9th planet in the solar system. In addition to photographing Pluto, the probe also sent tons of information that had served to discover all the mysteries of this celestial body. Thanks to this, today we know that Pluto is a vast ball covered with ice with recent geological activity and that it could contain water. After the Pluto flyby, the New Horizons probe continued its journey to the solar system's far reaches. To date, no other mission has managed to reach this distant world. Why is it challenging to get to Proxima Centauri? Proxima Centauri is the closest star to the solar system. However, with modern technology, it would take thousands of years to reach that star. Will we ever have the technology to reach the closest star to the solar system? For years, this star has been observed with the most powerful telescopes in the world, and thanks to this, we have discovered that the star Proxima Centauri has at least one exoplanet that could have the conditions to host living beings. This makes reaching this star a matter of great importance for humanity, since this distant world could have living beings or be a human settlement in the future. But how difficult would it be with modern technology to get to this star? In short, a lot. It would be tricky. It would be the most challenging feat that the human race could perform in the distant future, and one of the most important if it were to be achieved. Suffice it to say that in the modern era, even with the technology we have not managed to send a spacecraft out of our solar system, nor have we taken humans beyond the moon. Not a human being has set foot on another planet other than Earth, so you can be entirely sure that there is still a long time before we manage to send the first spacecraft to Proxima Centauri. But how long precisely? Do we have any estimated dates for when we might reach this star? Let's see what the science says about it. So close and so far. The fastest human-created object we've ever launched in the solar system is Voyager 1. This venerable probe moves away from the Sun at a speed of 17.4 kilometers per second, equivalent to about 540 million kilometers per year. But Proxima Centauri is 4.24 light-years away. At this speed, it would take about 76,000 years for Voyager 1 to reach Proxima Centauri, assuming it traveled toward it, which it doesn't. To reach Alpha Centauri within an acceptable time, the speeds we have to reach must exceed 10,000 kilometers per second. At that speed, we would arrive in 130 years, which can be somewhat annoying, considering that most humans die before the age of 100. If we travel at 25,000 kilometers per second, the flight time is reduced to 50 years. Half a century is not wrong for an interstellar trip, so this should be the speed we aim to achieve. A challenge if we remember that Voyager 1 moves at less than 18 kilometers per second. Clearly, we have no choice but to use propulsion systems other than the usual ones. So we better forget about the conventional chemical propulsion used by ordinary rockets. Why? Because if we want to reach 1% of the speed of light, or 3,000 kilometers per second, using conventional chemical rockets, we would need 1,026 kilograms of fuel for each kilogram of mass of the ship. That is, the ship going to Proxima Centauri would have 100 times the mass of Earth, something completely impossible. On the other hand, if we want to travel to Proxima Centauri in this century, we must make certain sacrifices. For example, forget about human crewed spaceships. Conventional space probes are infinitely cheaper and more powerful. In addition, we can conceive of a mission limited to flying over the Alpha Centauri system without breaking and entering orbit around one of the two main stars, which would mean enormous energy savings. What propulsion systems can we use? Ion and nuclear thermal propulsion. Electric propulsion, ionic or plasma, is currently used in several spacecraft and allows a specific impulse to be achieved for hundreds of hours. Nuclear thermal propulsion follows a bit further back. These propulsion systems are not bad for traveling through the solar system, but it would take 40,000 years to reach Proxima Centauri. It would probably be better to rule out these options now. VASIMR, Variable Specific Impulse Magnetoplasma Rocket. This engine was created by Ad Astra Rocket Company, led by former Costa Rican astronaut Franklin Chang Diaz. The project intends to create a plasma ion engine that will serve as a cheap and efficient alternative as a propulsion power source for spacecraft. He mainly focuses on exploring other parts of the solar system, such as a possible trip to Mars. With this technology, the journey would be 10 times faster than the current one and enable manned trips to the Red Planet, reducing the time from 18 months to approximately 39 days. Let's assume that, despite complaints from many critics, VASIMR is an economically viable project. In that case, a spacecraft with the VASIMR engine would only take 2,200 years to reach Proxima Centauri. It's certainly much less time than using ion propulsion, but it's still overcoming the 1,000-year barrier, and unfortunately humans don't live that long, so this option is ruled out. Pulsed nuclear propulsion. Popularized by the Orion project of the 60s, this system seems like something from science fiction. But the truth is that the associated technologies have already been tested. A pulsed nuclear spacecraft moves by detonating nuclear devices a short distance from the vehicle. A special plate absorbs the shock wave with shock absorbers, which transfers part of the energy to the spacecraft so that it accelerates constantly. Orion was a perfect vehicle for traveling through the solar system, but this system is not so attractive for interstellar journeys. To begin with, nearly 300,000 detonations of nuclear fusion bombs, and not nuclear fission bombs as in the original Orion project, proposal would have to be used, which is quite possibly beyond our technological possibilities. An interstellar Orion project with a human-crewed spacecraft would have a mass of 400,000 tons and a plate 100 meters in diameter. And even with these monstrous dimensions, it would take about 150 years to reach Proxima Centauri. Not bad for a generational spaceship, but it doesn't seem to be best suited for an automatic reconnaissance mission. Even so, it is a system to consider if we join it to other forms of propulsion. Solar sails. In the language of interstellar flights, a solar sail is not a simple photonic sail like that of the Japanese Space Agency's Icarus space probe. A solar sail consists of a vast parachute-shaped structure that, like a photonic sail, would use the radiation pressure of sunlight, and not that of the solar wind as is sometimes mistakenly believed, to accelerate the spacecraft to escape velocities from the solar system. But to take advantage of this system, it is necessary to deploy the sail near the sun. Assuming that in the next few decades we will be able to build giant ultralight sails capable of withstanding more than 60 Celsius of acceleration and thousands of degrees Celsius, a solar sail could travel to Alpha Centauri in 1,000 or 2,000 years. It is still long, but you can combine the system with others to decrease flight time. For example, the Medusa proposal of the 90s linked pulsed nuclear propulsion with a solar sail. In addition, an interstellar spacecraft could use a solar sail to visit Proxima Centauri and then maneuver to travel to Alpha Centauri A or Alpha Centauri B. Solar sails are an exciting technology for interstellar travel, although these are still in a primitive stage of development. If in the future we manage to develop them and make the most of their benefits by combining them with other technologies, they could be the ones we use for the first trip to Proxima Centauri. Laser candles. Laser sails are a specific case of propulsion systems using energy beams. These consist of a giant photonic sail propelled not by sunlight, but by a set of powerful super laser beams in Earth orbit or some point of Lagrange. Suppose we had a set of space lasers, 25 gigawatts of power. In that case, we could send a 100-kilogram ship, of which 33 kilograms would be the payload and the rest the sail, to Alpha Centauri in only 40 years. A fairly reasonable time considering that the Voyager spacecraft have been traveling non-stop through the solar system for more than 45 years and have not yet managed to leave. The lasers should constantly work during the 4 decades that the mission would last, and the sail would be limited to flying over the system. Still, we are facing a form of propulsion within the technological possibilities of our civilization. Of course, 100 kilograms is tiny, but if we use a slightly more massive ship, the flight time will shoot up to 100 years if we do not increase the power of the lasers. So initially, this technology only serves us for uncrewed missions. Although we cannot send humans to other stars with this technology, at the moment, this is the most promising method in the short, medium, and long term. Starshot Project. As surprising as it may seem, although reaching Proxima Centauri seems an impossible mission to achieve for modern technology, there is currently a research and engineering project developed by the Breakthrough Initiatives program that aims to develop a fleet of micro spacecraft, known as Starship, powered by solar sails capable of traveling to Alpha Centauri at 15% or 20% of the speed of light. That is 60,000 kilometers per second. So it would take between 20 and 30 years to reach its destination and another 4 years to communicate to Earth its arrival. The trip would also include a flyby of the planet Proxima Centauri b, which has characteristics very similar to that of Earth and is also in its star's habitable zone. The central concept that would allow this project to be launched is explained in the article Work Plan for Interstellar Flight, published in April of 2015 in the scientific journal British Interplanetary Society by Philip Lubin, a researcher at the University of California at Santa Barbara. The concept of Starshot consists of the launch of a mother ship with a load of thousands of nano spacecraft, a few centimeters in size and a few grams in weight, which, when they reach a high-altitude orbit, will be released into space. Then, high-powered lasers placed in Earth's orbit would focus a beam of light to propel the spacecraft sails individually and accelerate their maximum speed in minutes, achieving an average of 100 kilometers per second squared, and an energy of 1 TJ blown into each sail, each one 4 by 4 meters. Suppose the spacecraft finds a planet with characteristics similar to Earth in an orbit of the habitable zone of Proxima Centauri system, a case that occurred with the ground-based telescopes at the end of August of 2016. In that case, the project will try to bring the nano spacecraft closer to a distance of 1 astronomical unit, or 150 million kilometers or 93 million miles from the planet. At that distance, the spacecraft's cameras can obtain graphic data of a high enough quality to know these characteristics. Each spacecraft would have the possibility of transmitting data to Earth using a compact laser communication system. The swarm of thousands of units would compensate for the possible loss of spacecraft caused by collisions with interstellar dust during their long journey. Although this project is currently still in the development phase, it is estimated that with adequate funding, it would be possible to make it a reality in just 2 decades. That is, we would be able to see the execution of a mission and the arrival of the first spacecraft to Proxima Centauri in the same century. But even if we don't discover planets or moons like Pandora from the movie Avatar in the habitable zone of Proxima Centauri, a trip to the nearest star is a significant challenge for humanity. A challenge that would allow us to understand better the processes of planet formation in the Milky Way, and in the process, understand how our solar system was formed. As Carl Sagan said, by the time we can visit other stars, we will have changed. Only a mature and brilliant species can face the vast abyss of interstellar space and overcome it. If we want to survive in the immensity of the universe and not fall into oblivion, humanity must travel to the stars. It is in our hands to make this dream come true. Will we be able to meet the challenge?